When the soil is exhausted, the silence is heavy. Imagine standing in an empty silo, waiting for a harvest that will never arrive. To understand why the harvest fails, we have to look inside a single grain of wheat. Every living organism relies on a specific chemical backbone to hold its DNA and RNA together, and to transfer energy using a cellular molecule called ATP. That backbone is built from a single, finite element, phosphorus. Because of its slow biogeochemical cycle, phosphorus is exceptionally scarce in the natural environment. Biochemist and science fiction writer Isaac Asimov observed this mathematical limit and gave it a precise name: life's bottleneck. It is the strict limiting nutrient for organism growth across all terrestrial and marine ecosystems. You cannot synthesize this element in a laboratory, and you cannot substitute it with another material. If the supply of phosphorus stops, biological reproduction mathematically halts, rendering all other existential human threats entirely secondary. Humanity has always been tethered to this biological reality. In the 19th century, South American nations fought bloody naval wars over the Chincha Islands. The prize was millions of tons of guano, seabird droppings rich in the phosphorus and nitrogen needed to replace dying soil nutrients and maintain crop yields. The pressure to secure fertilizer was so severe that in 1856, the U.S. Congress passed the Guano Islands Act. It empowered American citizens to annex nearly 100 uninhabited islands in the Pacific and Caribbean just for the right to mine the bird droppings, laying the legal foundation for an overseas American empire. Today, we assume high-tech agriculture has insulated us from this kind of raw resource scramble. We point to GPS-guided tractors and genetic engineering as proof of our independence from nature. Yet, those innovations only dictate how efficiently we spread the fertilizer. The underlying math remains identical. Our advanced civilization requires a constant, massive influx of finite terrestrial dust to survive, leaving us just as reliant on the Earth's crust as those 19th century empires. This map shows the current global distribution of economically viable phosphate rock. Notice the intense concentration in North Africa. Today, Morocco and the Western Sahara control approximately 75% of the world's remaining viable supply. A single state-owned entity, the OCP Group, coordinates this extraction. They move hundreds of millions of tons of earth in open-pit mines to supply the raw material that maintains baseline global agriculture. Now, that same finite rock is being pulled into the electric vehicle transition. Lithium iron phosphate, or LFP batteries, are rapidly dominating the global market. We are forcing a direct competition between the materials needed to power our cars and the nutrients required to grow our food. By consolidating the absolute requirement for both global food security and the energy transition into a single geographic region, we have created a structural vulnerability far more concentrated than any fossil fuel network in history. We extract this highly localized resource and feed it into a system defined by linear consumption. Between the initial mining process, transport, and agricultural application, roughly 80% of the phosphorus we pull from the earth is lost or wasted, washing directly off industrial fields. When that nutrient-rich runoff hits freshwater, it triggers eutrophication. The sudden abundance of phosphorus causes an explosive, toxic overgrowth of algae on the water's surface. As these massive algal blooms die and decompose, microorganisms strip the dissolved oxygen from the water, creating hypoxic dead zones where aquatic life suffocates. The remaining phosphorus then drifts down, settling permanently into the dark, irretrievable ocean floor. We are actively bleeding the Earth's limited geological lifeblood into the sea. Through sheer inefficiency, our food production system converts our most precious survival asset into a toxic marine pollutant. This chart shows the peak phosphorus theory. It applies the Hubbard curve to phosphate rock, demonstrating that global extraction must eventually hit a maximum rate before finite geology forces a terminal decline. As we move past that peak, the extraction process becomes increasingly difficult. Mining companies are forced to process declining ore quality, spending massive amounts of energy and capital to filter out heavy metal contaminants like cadmium and arsenic just to maintain a usable supply. We currently rely on the volume contained under this curve to feed half the global population. 4 billion human beings exist today solely because of the artificial crop yields generated by this mined rock. You cannot replace phosphorus with software. You cannot write an algorithm that generates a biochemical backbone out of nothing. We are bound by the hard limits of chemistry. When the economically viable rock runs out, the crop yields collapse. We spent the last century mastering rockets and microchips, convinced we were engineering an escape velocity from our natural constraints, but we neglected to secure the fundamental biological math required to stay alive on the ground.